Okay, yesterday we talked about Rolles theorem, and today we're going to talk about mean value theorem. Mean value theorem, you'll notice some similarities between them. If f is continuous on the closed interval, and if it's differentiable on the open interval, those are the two cases we had to have yesterday, then there exists at least one number in C where the derivative, the slope of the tangent line, equals, hopefully you recognize this as the slope of the secant line. So this, I'll go ahead and write that in there. The slope of the tangent is equal to the slope of the secant. It's much easier to see these again in pictures, so I've got some pictures drawn. This is mean value theorem. Notice how it is continuous on the closed interval and differentiable on the open interval. On both cases, continuous on the closed interval and differentiable on the open interval. This is the big part. The slope of the tangent, okay, so we're looking at tangent lines to the curve, is the same slope as the slope of the secant. So if you look at these pictures, I've drawn in right here the slope of the secant. Look how the slope of the secant, approximately right here, the slope of the tangent is equal. So there's one value of C in that case. On this next one, I neglected to draw in the secant line, so I'll do that really fast. So I'm looking at points where the slope of the secant is the same as the slope of the tangent. So it looks like that one I got off a little bit, but you guys would see that there's three values, and these are all approximations of that. So there's at least one number in that closed interval where that takes place. There could be more. Let's have a little discussion about what this really means. So what mean value theorem is really saying is basically if you were on a trip and you traveled an average speed of 60 on the trip, then at some point during that trip you must have at least traveled 60 miles an hour. So at some point along that trip, if you were averaging 60 miles per hour, you had to have been going 60 miles per hour at least once during that trip. Notice that Rolles theorem and mean value theorem are very similar. It's just Rolles theorem is a special case of the more general mean value theorem. Remember, Rolles theorem requires three parts to its if. Not only does it need to be continuous and differentiable, but it also has to have f of a equaling f of c. And in mean value theorem, f of a is not equaling f of c. So on this first example, what we're going to do is we're supposed to copy this graph, and then we're going to sketch the secant line. So I'll do that with a highlighter as best I can, or maybe I'll just do that with but I think a highlighter might be better. If I had a straight edge, it would make it way easier. So there's my secant line, and what I'm supposed to do is find points where those tangent lines to the curve are the same as the secant lines. So I will do so. I'll approximate that there's a C value about right here. So straight down, there's one C value. It looks like there's another C value right here where the slope of the tangent equals the slope of the secant. I'm not drawing that very straight, but there's a second value. And then there looks to be one more value about right here. So maybe this is C3. So we have now sketched any of those tangent lines to the graph that guarantees the mean value theorem. This next problem, we're supposed to explain why the mean value theorem does not apply to this open interval. Well, I'm going to just look at a graph in order to do that. This actually tells me to shift the absolute value graph 3 units to the right. So this is just a general sketch of what that looks like. I can see that mean value theorem does not apply because it is not differentiable at 3. So mean value theorem does not apply because f is not differentiable at x equals 3. This next problem, we're going to determine whether mean value theorem can be applied. In order to do that, I need to meet its two requirements, that it needs to be continuous on the closed interval and differentiable on the open interval. This one is simply So, because it's a polynomial, so we're going to state that. So when we're trying to show that it's that it can be applied, we'll go ahead and use this statement. F is continuous on the closed interval 0 to 2 and differentiable on the open interval 0 to 2 because it's a polynomial. Therefore, we can abbreviate this, MVT by mean value theorem, there exists a value or values x, and I'll just put an x value, I'll just put blank because we don't know where it's at, where f prime of x equals the slope of the secant, which would be f of 2 minus f of 0 all over 2 minus 0. In order to figure out where that occurs, we're going to have to find the derivative. So off to the side here, I'll find the derivative. And the derivative would be 4x cubed minus 8. Now what we want to do is we want to use that idea and set up an equation in this form up above. So the derivative 4x cubed minus 8 equals f of b, which is f of 2 minus f of 0 all over 2 minus 0. I'm getting those values here. This is my a and this is my b. So what is the value of f of 2? F of 2, when I plug 2 in there, I get 16 minus 16, which is 0. Minus plug in 0 up here, I get 0 all over 2 minus 0. So really I'm just looking at where is 4x cubed minus 8, and I'm going to go ahead and factor out that 4 right now. So where is 4 times the quantity x cubed minus 2 equal to 0? And that would mean when x cubed is equal to 2, it would be equal to 0. So the x value is the cube root of 2. That does fall within the interval, so I know that I can go ahead and fill in my blank there. There's an x value at cube root of 2. This next problem, determine whether mean value theorem can be applied. I can see that I'm talking about this interval right here, and f is not differentiable. I should say this first of all, it's not continuous at x equals 0. So mean value theorem does not apply. Does not apply because f is not continuous at x equals 0. This last example of mean value theorem tells me to use a calculator. You guys can use a calculator, but it is really not necessary. It is just a nice check to use your calculator. I'm going to show you how you can do this without a calculator at all. Anytime they ask you to do calculator problems, they may require you to use a calculator, and sometimes they don't. But as I said, it's just a nice check. What we're going to do is we're going to first find the slope of the secant line. And we'll do that by taking f of 6 minus f of 0 all over 6 minus 0. When I plug in 6, I'm just going to tell you, you get 900. Take my word for it. You guys can check it. Plug in 6. 6 to the 4th minus 2 times 6 cubed plus 6 squared gives you 900. Minus 0 all over 6 minus 0. So what that means is that the slope of the secant line is 150. Now, what it's asking me to do is find and graph the secant line. Well, I now have the slope of the secant line. I haven't written the equation for the secant line. The equation for the secant line can be found by finding a point that's on the graph. So we'll just go ahead and use 0 because that secant line is going through 0 comma something and 6 comma something, and I'll just plug in 0. 0 flat out gives me 0, so that's the easiest thing to find. So the equation for the secant line has a point 0, 0, and we now know that the slope is 150. So I could write y minus 0 equals 150 times x minus 0. So more simply, my equation, my secant line, is y equals 150x. So I've taken care of finding the secant line. Now the next thing I'm supposed to do is find and graph any of the tangent lines of the graph f that are parallel to the secant line. So in order to find those tangent graphs or tangent lines to the graph, I need the derivative. So the derivative is 4x cubed minus 6x squared plus 2x. We're going to set this equal to the slope of the secant line. So this is the slope of secant line. Remember, we want them to be parallel, any of the tangent lines to be parallel to the slope, so we're going to set them equal to each other and find out what x values this occurs. Now, in order to solve this polynomial, we want to go ahead and move everything to one side of the equation. This is not factorable, so we need to use our calculator in order to do this. So I said that we wouldn't need a calculator, and I guess I was mostly meaning to the picture part. But we do need the calculator to help us solve for the x value. I'll be happy to show you how to do that if you've not learned how to solve for an x value on your calculator. Just for right now, you need to just trust me in knowing that I use my graphing calculator to find that the x value at which this is equal to 0 is approximately 3.872. When I go ahead and find the point that goes along with this, because I need the equation of the tangent line, I find out that my y value is 123.672. Again, you guys can check all that stuff with your calculator by plugging in 3.872 into this function. I'm not going to take the time to do so on this video. So that means the tangent line equation would read y minus 123.672 equals 150 times x minus 3.872. And I've accomplished my goal. I found the equation for the secant line and I found the equation for the tangent line.